In today's topic video, we're going to be talking about how you can interpret integrals as the areas underneath a given curve. Let me show you an example. So say we had on the xy plane some curve that looked like this. And just for the sake of example, let's say that I cut the curve right here. And so these are going to be at the points A, B, and C. And let's say I'm trying to figure out what the integral is from A to B. So I write that down as the integral from A to B. And let's say that this curve I drew right here is f of x. So we're doing the integral of from A to B of f of x dx. Well, what that would be is it would just be this area right here. So if this shape that I've got here that I'm sketching in blue, if it was possible for me to find this area geometrically, then I could just find that area geometrically. I could just use geometry and figure that out instead of doing the integral of whatever this function is. Now let's say I wanted to add the integral from B to C of f of x dx. Well, now that area is going to be right here. And so if I could just find the area of this plus the area of this, that's the same thing as taking the integral of this section plus the integral of that section. So again, just hammering in visually that integrals are area under the curve. And you may notice that the way I've drawn this could also just be one whole integral from A to C, the way that this is drawn. And yes, you could do that. So I could just say this is the integral from A to C of f of x dx. And that can be very useful if you want to save yourself some work. And you notice that these sections are connected and it's the same curve. Of course, if these were different curves, like if this was an f of x and this was a g of x, then I couldn't do that because I wouldn't be integrating over the same thing. Now, the only thing that you have to be really careful of is that when you're interpreting integrals as areas, remember for geometry or like in the real world, area is always a positive number. Like the area of this screen in front of me is positive. But if I've got a function in the xy plane, it's totally possible that this function could do something like this. And you can notice that while I do have some positive area here and here, I've also got negative area right here. Now, negative area doesn't really make sense geometrically, but mathematically, it's fine. I'm just adding a negative sign to that number. So what would happen if you did the integral, let's say this is still just a function, I'll call it g of x. We'll just say this whole thing's one function. And let's say this is the point A, B, C, and then D. Well, you could, of course, just do the whole integral from A to D of this function, and that would give you your answer. But what if we wanted to do this geometrically like I was talking about? Well, what we'd do is we'd have to find the areas of each little bit. So first we'd have this area, which would be the integral from A to B dx. Let me skip B to C for a moment. Let's talk about C to D. I would add that area. And then I would add the area from B to C. Now the thing is that the integral, if I just did the integral from B to C, it would give me a negative value. So if I'm writing it as an integral, I would still put plus for that section. But what would happen if we just call this, say, area 1, area 3, and this area 2, then what this is it's area 1 plus area 3, but it's going to wind up being minus area 2. So if you have a way to just calculate these areas using geometry, you have to keep track of this yourself and subtract out any areas which are below the curve. And so that's why usually if we're trying to clarify that an integral can be interpreted as area, you'll hear it said that it's net signed area, meaning that it's after you do all your integrals and you add and subtract different areas, you could get a negative number. And so then just saying it's area may not make sense, but we can just say it's signed area. And if you're using terms like that and you're comfortable with them, it's assumed that it's because you understand what's going on here, that this curve could dip below the x-axis, and so some of this area gets removed. So that's just a general overview of the idea that integrals fundamentally for the xy plane are areas underneath these curves. It's just you've got this weird thing where if the curve goes below, you get negative area, and it's kind of unique to integrals. And so that is this general topic.